Okay, so we'll say welcome back to recursive functions. Okay, so this is another type of sequence we could have. It's something called its recursive sequence, which means you are given a number of starter values, and then the values following that are going to be defined, are going to be dependent on the starter values that you had. Okay, so let's see. One of the more famous ones is something called the Fibonacci series. Where they give us the A1 is 1, A2 is 1, and then AN is equal. These are harder to kind of predict what the end, what if I asked you like, what is A sub 103? You would be right to curse me because you'd have to pretty much go through what's going on here to get this. So what this means is that the third value, right? So A1 is 1, A2 is 1, and then A3 would be the first one, right? 3 minus 1 is, or 3 minus 2 rather is 1, plus the one previous to that. So it's the two previous entries. Okay, so A4 is equal to, right, 2 plus 1. A5 is going to be 2 plus 3, and so forth. This is a pretty famous sequence. You may have, if you had an art class that was anyway kind of mathematical, you may have learned about the golden ratio. Okay, this is called the golden ratio. We use the symbol of phi or phi for it. But that's what this is, okay? And it's supposed to be the most aesthetically pleasing rectangle. And if you, I'll reference this thing. Donald Duck in Math Magic Land, okay? If you reference this, they show you all things about the golden ratio. And there's a lot of people that still believe this, and they teach it as if it's a thing. And it was for a long, long time. We thought this was the way it was going to work for a very long time. I can't remember the name of the guy, but there's a YouTube video of a professor from Stanford who's talking about whether or not things are really the golden ratio. And he puts a bunch of rectangles up on the screen, and he's like, pick the most aesthetic one. It's like, no, I'm not going to do that. So it's nice to make like nice little things, but he also noted that the way that people drew these things was like they drew the boxes like this around the golden ratios that they were doing, and you could see with this thickness of a rectangle, there's lots of values that could be, maybe it's this one, but maybe it's something close to this one, and maybe it's something that's maybe not so close, depending on where this one's supposed to be. So that was a pretty good video. So if you ever have a class where you have to like deal with golden ratio, I'm going to recommend like play nice and allow what they're teaching to be the thing, because it's not a bad method, but take it all with salt, because I don't think that we have a aesthetically pleasing rectangle. Like, what is the most aesthetically pleasing rectangle? I just don't see it. But mathematically, good series, lots of things, and there's lots of things that do actually follow this thing. Like there's honeycombs, there's flowers, lots of stuff in nature starts building. Like you come up with 1 and then 1, and then the next step is to go off of the previous 2 things, and then to go this way. So it does happen in nature. You will see this. In art, maybe a little bit more skeptical, but in nature, this actually, you will see this symbol, and like how seeds get put into a sunflower kind of a thing. Okay, so there's a lot of study on golden ratio. If you ever take like liberal arts for math or math and art, they're going to do this a lot. Okay, but that's not the only one. That's the most famous one, but it's not the only one. We can do recursive on 1, 2, or 3 values. They just have to give you one before they start. Okay, so just be sure that sure that that's going to happen. So let's see here if I can find my little examples with these guys. Oh, that's right. I stopped writing them. So we could do an example or two. Okay, so in this case, right, they give us the first one. They say a is -3, and then 3a to the n minus 8, 3a sub n minus 1 plus 7 is going to be how to generate the rest of these. Okay, so how would you do that? So we have a1 is equal to -3, a sub n is equal to 3a(n minus 1). Is it plus 7? Plus 7. And by the way, here's where you're going to see, like, oh, well, the first 3 terms look pretty easy to predict, and then it just goes completely off the rails. So we'll say a1 is equal to -3, a2, right, is equal to 3 times the previous one plus 7. So that's going to be -9 plus 7, that's -2. So with -3, -2, a1 is going to be 3 times -2 plus 7, so that's going to be -6 plus 7, it's -1. See, that looks pretty tame, right? If I gave you a series, I said, oh, or a sequence, I would say -3, -2, -1. What's the next one? So let's see, that was a2, a3, a4 is 3, -4. Or, yep, there we go. So 3, -1 plus 7. Okay, so this was going to be -3 plus 7. You all guessed 4, right? When I guessed the next one. So -3, -2, -1. 4 was the obvious answer, right? So I said, be careful with things like that. I mean, not that anybody's life or death is going to ever matter about that, but it's one of those things where you don't necessarily have to. You're not necessarily going to be able to predict it. Okay, but that's pretty much what you do to figure out a recurrent series. There are some more advanced techniques that you can generate, like a to the n as a general solution. Like you'll be able to get the values for it. That's a class called difference equations. And to be quite honest, I didn't really understand it when I was taking it. It was kind of cool, but it's been a while, and yeah, it was a little bit out there. So a1 was -3. This was -2. This was -1. And if you said, I know what the next one's going to be, 4. Okay. And then what do we have? 19. I hope this doesn't make a liar out of me. No, didn't like that at all. Let's see. Did I get the thing right? I got 3n minus 1 plus 7. Let's see. A3. So A2 is correct. So this was 3. Oh, did I? Yeah, 3 times -2 is -6. -6 plus 1 is... I don't know why it ran off the rails for that one. They didn't skip any. Oh, yeah, 7 minus 6 is +1. All right. Well, let me in your checkbook today. It's +1, so we end up with 10. Oh, how embarrassing. Okay, 3 times 10. 7 is going to be 37. Okay. I meant that. Maybe not. All right. Yes, watch your signs is always a good piece of advice. So write the first 5 terms of the sequence defined recursively. Write them as a fraction when applicable. Very good. All right, let's see if I can redeem myself here. So we gave A1 is equal to 12, and AN is equal to 1/4, AN minus 1 minus 8. All right, so A1 is equal to 12, A2 is equal to 1/4 times 12 minus 8. So that's going to be 3. 3 minus 8 is minus 5. So you can see where this is going to go off the rails quite quickly here. A 3 is 1/4 times negative 5 minus 8. And I'm not gonna attempt it. Just gonna think, well, let's see what we have here. We have negative 5/4, negative 5/4, right? Minus 8. That's not right. So we have negative 5/4 minus 8. And again, they're going to want it as a fraction. So we're going to go ahead and write this as negative 37/4. Okay. A 4 is 1/4 times negative 37/4 minus 8. So I'd like to do a little bit here. 37/16 minus 8. Okay, so we have negative 37/16 minus 8. And, oops, I don't want to do that. I just wanted to do this. So negative 165/16. Okay. And then A5 is 1/4 negative 165/16 minus 8. So negative 165/16 times 4 is 64 minus 8. So negative 165/64, enter, minus 8. And then second function, no, not second function, just math. Negative 677 over, what do we have here? 64. All right, so let's go ahead. So got the easy one. And I believe the second one in the series was, okay, it's negative 5. All right. And the one after that, so you can make up your own Facebook little quizzes here, because nobody's going to get these. Negative 37/4. Negative 165/16. All right. Negative 677/64. Negative 677/64. Crossing my fingers that I did my arithmetic correctly. All right, that one looks better. Okay, we're good. All right, so those are recursive functions, recursive sequences. They are kind of neat in computer programming. They use them a lot, so they're good to know. And so there's a very famous one. Nope, not quite. Let me go back by one. One more. Start with an easy one. Good. Okay, so the next idea for this is series. Okay. Actually, I'm going to go back and do this again too. I'm going to say stop recording, and then I'm going to start it again.